with a negative state of the negative charge of the polymer change, and in a way open this and leave lithium to get out much more easily. Actually, this was an idea which came out from our lab. We published that in an important journal. And you see from this Arrhenius plot that this is the conductivity of the normal PO, this one. And this is very similar to the one that I showed you before, one you see here. This is this one, all right, about 10⁻⁴ to 10⁻⁶. And here, 10⁻⁴, 10⁻⁶. But if we add some of these ceramics, we raise the conductivity almost 1 order of magnitude. And the break also is happening at a temperature a bit lower. This was a good result, but of course is not sufficient to allow this polymer electrolyte to be used for lithium batteries devoted to maybe to the electronic market. You cannot have a cellular phone which works only at 60 degrees. However, this can be used to develop batteries operating at temperature higher than 60 or 70 degrees. For instance, batteries that are devoted to the electric vehicle. There in a vehicle, the engine will by itself produce enough heat to let the battery to operate. And you see here, in fact, that this idea has been taken now, and there are some company producing a all-solid-state lithium-ion polymer battery. In this case, obviously, this battery has used this polymer electrolyte, but not a lithium metal, but maybe a graphite. And here you see that the charge and discharge of a battery using, well, maybe this is not lithium, as I say, but let's say lithium, and the lithium iron phosphate, which cathode that we discussed in detail in the past, operating around 3.5 volts. And in fact, you see that the battery does operate. I think this battery operates at 90 degrees, I think. I've not written there, but we have a good cyclability. Oh, I forgot about, you have also ionic liquid. Okay. The third category of electrolytes are the ionic liquids. What are the ionic liquids? These are molten salts at room temperature. I told you before, maybe I can go here. Yes, I told you before that if we heat up sodium chloride about 800 degrees, we have the decomposition of the salt, and the salt, which is a solid at room temperature, becomes a liquid, because now we have separated sodium and chloride. But you see that the temperature of fusion depends on the type of an ion. So for instance, if we move from, excuse me, a type of an ion and a type of cation. Now, if we move to a bigger anion like cesium, we drop in temperature. Then even bigger one, we go down and down until maybe in some cases we have some liquids even at room temperature. And the basic idea, in fact, is to mix a large cation, which interacts very little with an ion, and like imidazole type, with flexible anion, then this combination is produced in a liquid. But of course, in this case, you don't have any lithium conductivity. So to make this ionic liquid useful for a lithium-ion battery, you have to add some salts, like in a normal solution. And you see here from this graph that we have many combinations of this cation and anion. And this is a very good feature of the ionic liquid, because according to the application, you can change the composition. For say, this is the melting point. You see, for instance, that if you have the combination of this one with this one, the melting point is very low. Or you can have a much higher melting point. It depends really on why you want to use for what you want to use these ionic liquids. So you see the ionic liquids are of course material which have weak interactions, and the weak interaction, why weak? Because if they're weak, they separate very easily, and is due to large cation and anion delocalization, and low tendency to crystallize due to the flexibility of the anion and the symmetry of the cation. And there are some examples. For instance, you can use as a cation N-butyl N-ethylpyrrolidinium, TFSI, and this is N-butyl N-ethylpyrrolidinium, which we can indicate as PI24. As an anion, very popular one is NN-bis-3-fluoromethansulfonyl imide, TFSI. So the ionic liquid is PY24 TFSI. The most important thing is that these ionic liquids have very high thermal stability. You see, for instance, water down here has only, of course, 100 degrees. When you heat water 100 degrees, you boil it. You make coffee, tea, or spaghetti. Depends. So you're coming from America, England, or Italy. But if you go in ionic liquid, you have very large stability. This is very important, because that means that if we use this ionic liquid in a cell, even if the temperature of the cells goes up to 400 degrees, there is no effect, high safety. And this is demonstrated also by this TGA curve. You know what the TGA analysis is? You just rise the temperature and see whether there is a weight change. So it's something decomposed. Of course, the weight changes because the material decomposes. And for using one of these, maybe this one that we had developed in our lab, you can see that we can go up to 350 degrees before you have any decomposition. And this is also demonstrated here. I think I showed this last year as well. You can use flame on this ionic liquid, nothing happens. If you do the same with a normal lithium battery solution, they go into flame. And of course, when we add some lithium salt into the ionic liquid, the conductivity is decreasing because we increase viscosity. But still, even a reasonably high concentration, because you have a 0.4 molar, the conductivity remains higher than millisiemens, so conductivity is not really a problem because it's the same, more or less the same value of the standard electrolyte. So there are some very promising features here. They make these ionic electrolytes, ionic liquids, very promising electrolyte for batteries. There's no flammability, so there's no chance that by when you use this ionic liquid, your battery can go into flame. very important. Second one is the same thing, high thermal stability. And these are, most of the time, these are, the compounds are compatible, not toxic, and the conductivity is quite high. But we have always problems, otherwise it's not fun, right, in the research. And the problem is that the stability window of this electrolyte is good at the anodic side, so you can use all the cathode that you want. It's not that good at the cathodic side. So maybe it is very difficult to use with these ionic liquids, for instance, lithium, metal, or graphite. But work is in progress on that. Okay, let's summarize now all the situation. And you see, we start with the liquid organic solutions. Their advantage is to have high ionic conductivity, and the liquid state make them easily to operate. But they have some problem with the stability window and safety. Gel-tight membrane, the advantages are high conductivity in a wide temperature range, and I forgot to add here, of course, the plastic configuration. The issues are the fact that some of the liquid can be released, but this issue may be solved by dispersing some. You don't have this table there? Yes, you are. Dispersing some additives. These are the most important in view application. In fact, a lot of attention is still devoted to these materials, because they are solvent-free, fully solid configuration, and they don't cost too much. But we have, at the moment, some temperature-dependent conductivity. The conductivity goes down below 80 degrees. The conductivity of lithium ion, the transport of lithium ion can be a little low, but this can be solved. And also a problem here that I forgot to mention before is that the anodic stability of this electrolyte is around 4.4 or 4.5 volts. So you can use electrodes material which are within this stability, and this is the reason why the most common cathode used with this electrolyte is lithium iron phosphate, which operates at 3.5 volts. Ionic liquids are the electrolyte of the future. They are not flammable, they have very high thermal conductivity, they have very high thermal stability, high conductivity, so ideal in a certain way, but we have still to solve the compatibility with low voltage anodes. And I think this concludes, yes. And with this lecture now we have concluded the presentation of lithium batteries. So that from the next, for next Wednesday, we will start to work on fuel cells. And also we should have now consider when you will have the first test. So I will look at this, and on Wednesday we may discuss that. Okay? Have a good day.